Hello and welcome to my physics lab. Today we're looking at perfectly inelastic collisions. My name is Olumide Shonuga and I thought I'd go all out, with a face cam. So the main point of the lab is finding how much kinetic energy is lost when two cards collide and have a perfectly inelastic collision. And this energy is lost due to internal energy. For my result, I got 3.38 times 10 to the negative 2 joules in internal energy. Why did I choose this topic? In lecture, I saw that internal energy is kinetic energy final minus initial, and I didn't consider that there's heat and sound, which are part of the energy that is lost. So I found it quite interesting. So some important concepts. Like I just said, this is a perfectly inelastic collision because in the video, as you'll see, the cards stick together. And in inelastic collisions, perfectly inelastic collisions, momentum is conserved, but kinetic energy is not conserved. And this is because kinetic energy can turn into sound, it can turn into heat, so it's lost in the molecules. And these are the formulas I used. Here is internal energy, as I described, kinetic energy, and conservation of momentum, which we'll use later. Here's a video demonstration. I got this on the internet. So for my tracker analysis, I took the data, I took many points. I took about 50 data points, and as you can see in the graph, up until about 0.8 seconds, it's constant velocity, and then it somewhat halvens the slope, and that's because when the cards hit each other, the velocity decreases because to maintain momentum, when the mass is doubled, obviously the velocity has to halven or somewhere close to that to maintain the same momentum. And here are my initial and final conditions. So internal energy calculations and results. How much kinetic energy is lost to internal in the perfectly inelastic collision? Well, KE initial, we can calculate half m1 v1 squared plus half m2 v2 squared, and that's what I got. And then I subtracted it from the final, and I got 3.38 times 10 to the negative 2 joules. So what else is at play in our system? Well, heat energy and sound energy contribute to internal energy, which is important to acknowledge, and other energies, by the way. And there could also be air drag. There's no mention of air drag in the video, but we can assume there's some air drag, which is why the graph actually tethers off at the top. It looks more exponential. Yeah. Assuming no friction also, because if there's friction, that could affect our readings of velocity. And if there's no internal energy, the speed should halven. So we know there is some internal energy and some kinetic energy being lost because it would have gone from 0.662 meters per second to 0.331, but it went even below that because some energy was lost and velocity was lost. So some potential causes of inaccuracy. We're assuming there's no other forces on our system like air drag, like I mentioned. I did the tracker points myself. I'm human. As you can probably see, estimation of average velocity. Yes, I estimated it using the points on the graph. I took the time ranges I needed and I got the average. And then So if there's no external factors like work done on the system, the momentum is always conserved. This is due to Newton's conservation law, and because there's equal and opposite forces acting, so the momentum is conserved. And kinetic energy would be conserved because no kinetic energy is lost in elastic collisions. How fast would car 2 need to move for the speed to be half v2? So this is the same formula we used earlier. M1 plus M2 VF is equal to M1 V1 plus M2 V1. Yeah, and that's conservation of momentum. And you set VF to have V2, and then you solve for V2. And there you go. That is all from me. Thank you guys for joining, and I'll see you in class.